In our journey towards making effective models, we'll always come across a scenario where we'll have to choose amongst the features that have been given to us to explain an outcome. And that's called feature selection, because not all the features provided to us are always meaningful. We have to find out the ones which are most important and retain them in our models. Thankfully, for this purpose, scikit-learn, the most famous library in machine learning, comes very handy. It has a specific module called feature selection, and that's what we'll be learning about today. So let's first understand what is feature selection. Feature selection is the process of choosing a subset of essential features from a larger set in our data set. The goal is to improve the model performance, reduce overfitting, and enhance interpretability by focusing on the most informative variables. These methods involve selecting relevant features while discarding the irrelevant or redundant ones. So what all techniques are we going to cover under feature selection? Let's go through these one by one. What are the popular approaches for feature selection? First is variance threshold. Next, we'll talk about the select k-best, then the recursive feature elimination, followed by select from model, and finally, sequential feature selector. And we've already discussed other approaches in the previous modules, like the approaches related to Pearson's correlation, keeping or dropping the features based on the correlation values, or keeping or dropping the features based on the variance inflation factor. We can also do principal component analysis, which is an unsupervised learning technique. But for this particular module, we are only going to concentrate on the first 5 techniques that we obtain from the feature selection module in scikit-learn. The plan is that we'll go through the theory part of each of these techniques, and then we'll perform hands-on in Python. Let's get started. So let's understand what's the importance of variance of a feature when we talk about predictive tasks. Let's say we're trying to solve a regression problem. We are trying to predict the income using the work experience. On the left, we have a plot where the work experience or the independent feature varies. It attains values anything greater than 0 to maybe 14 years of experience. Somebody who's a fresher to up to maybe 14 years of experience. And accordingly, you see the income also varies, more in a positive pattern. So in general, we can say as the work experience increases, the income seems to be increasing. But on the right, we have another plot where the independent feature or the work experience is constant. It does not vary. Everybody seems to have same work experience. So in this case, do you think work experience can be a good predictor of income? Because for everybody, work experience is one and the same. Till the income is varying. So we can't say that income is varying because of a variation in the work experience, because work experience here is constant. Obviously, income seems to be varying because of some other factor. So if a feature is constant, it generally doesn't play a very important role in predicting an outcome. This was the scenario where we took the independent feature as a numerical variable and also the outcome as a numerical variable. But let's just take another example where the independent feature is categorical and the dependent feature or the target is numerical. So we're trying to understand the difference in the income depending on the educational qualification. Let's say for a given company, there are 2 kinds of profiles. There are tech profiles and non-tech profiles. When you look at this plot on the left, what can you say about the income with respect to the educational background? If you pay attention, you'd see the tech profile people seem to have a median income which is higher than the non-tech profile. So this kind of indicates a difference. It suggests that it does make a difference as to what the educational background is. If it's technical, it seems these people are paid relatively better compared to the non-tech profiles. For a given organization, this is a hypothetical scenario. But let's look at the plot on the right. What can we say about this? For this organization, is there a difference between the technical and non-technical profiles? The answer is no, because their medians are nearly overlapping. You don't see a significant influence of the educational background on the income, at least for this organization. So once again, in which case do you think educational background has an important role to play? Well, in this case, the case on the left. Why? Because here you see a difference in the outcome depending on the choice of educational background. The case on the right says, irrespective of the educational background, the outcome doesn't change. So the variance threshold works on the logic that if the independent variable shows a constant behavior against the target, then it is not a good independent variable. It may be eliminated. So to put it together, variance threshold identifies and removes features with low variance. It operates under the assumption that features with very little variation in their values across samples are less informative for predictive modeling tasks. Once the threshold is set, any feature with a variance below this threshold is considered low variance and is therefore removed. We'll see this when we do the hands-on. Let's move to the next approach, which is known as select k-best. Select k-best selects top k. K is the number. So top k features based on univariate statistical tests. It operates on the assumption that each feature is independent and is evaluated separately. The selection is determined by ranking the features according to their scores from a specified statistical test, and then top K features are chosen. Let's understand this. So let's say we are trying to predict the sales or revenue generated by a company based on their ad spends. These days, every company focuses on digital marketing, and they try to reach out to their prospects through different channels. Some through Google Ads, some through Meta Ads, some through print media, some could be through other platforms. So this is kind of a linear regression equation that you see, that you're trying to predict sales using the spends on each of these categories. And there's a constant term also that we have in this equation, which is represented by this epsilon. So now let's take this equation and try to find out if we want to zero down to 2 categories of spends only. We don't want to be spending in 4 different categories. We want to reduce it to 2. Can we find out the 2 most effective channels that we should be continuing to invest on? This is the same equation that you saw on the previous one. In order to do this, we have to take every single feature, let's say Google Ad spend, and we have to check how strongly does it explain sales. Then we have to take the Meta Ad spend and see how strongly does it explain sales. So there would be scoring functions for each independent variable and dependent variable combination. Using that scoring function, we'll be able to find out a ranking. Now, the ones which get the best ranks will be the ones that will be shortlisted. Thankfully, all of this is done by the algorithm. We just have to give the appropriate input. So how does it work? We're going to calculate the independent statistical test for each feature. So to make it easier for you as to how we decide the right scoring function, here is a quick summary table. Let's say a target column is numerical, which is like sales, and the independent variable is also numerical, which is, let's say, the spend amount, Google Ad spend, Meta Ad spend. These are dollar values. So will again be treated as numerical. In that case, the scoring function is F regression, which works on the logic of simple linear regression. If the target column is numerical like this, but the independent variable is categorical, let's say we are talking about 3 different geographies. So these are categories. And now if you're trying to see whether this geography thing associates with the sales or not, the scoring function is F_classif, which essentially uses ANOVA inside. If your dependent variable is categorical, you're solving a classification problem, and the independent variable is numerical. So you're trying to solve, let's say, for a default or non-default, and the feature that you're using to explain that is credit score. Then you use something called as mutual info classif. It works on the logic of mutual information. And if both the variables are categorical, you're trying to predict defaults, but you have some kind of a category, which could be, let's say, the educational qualification of the person, which is a category, and the outcome is also a default, non-default status. Both variables are categorical, then you can perform a chi-square test of independence or dependence. So this is a quick summary to help you choose the right scoring function. In case of select K-best, you check how every single variable is associated with the target based on some logic. Now, if you have a mix of variables, some variables are categorical and some variables are numerical, you can segregate the variables by their nature and apply the appropriate scoring function. You can take all variables of the same nature at a time, and it'll come up with a ranking on those features and help you find out the features that you want to retain. Next is recursive feature elimination, and as the name goes, it involves eliminating the features recursively. So this is an approach where you take a model, let's say a logistic regression model or a decision tree, any of the models, and you fit that model using all the independent features. Let's say we had 10 features, but we wanted only 3 features finally. So we'll mention that we finally want to have 3 features. It'll create a model with all 10 features. Then recursively, based on a step size, let's say we choose 1, it'll keep on dropping 1 variable at a time until it reaches just 3 features. And these will be the 3 most important features based on feature importance or coefficients. We'll show this again to you in the hands-on piece. And next is select from model. So select from model selects features based on the importance or coefficients assigned to them by an external model. It again uses a model like recursive feature elimination, but it does not drop the features recursively. It creates a model using the features as provided and provides a convenient way to perform feature selection by leveraging the intrinsic feature importance information provided by certain model. The difference lies in the fact that it uses a threshold. So any feature with its importance or coefficients less than the threshold is dropped. What was happening in case of recursive feature elimination is that we were creating a model and we're dropping features one at a time. But in case of select from model, we are creating an overall model, and then based on the threshold, we are dropping whatever be the number of features less than the threshold all at once, not recursively. Finally, we're going to talk about sequential feature selector. Sequential feature selector again builds or removes the features based on the performance of a selected machine learning model. So all these are supervised approaches. They're using some or the other model to decide what are the features to keep. This process involves selecting or excluding features at each iteration, evaluating the model's performance and determining the best subset of features. So to give you an example, let's say we are trying to predict the same sales value or the revenue using the ad spends. So let's say we've taken a couple of features like Google ad spends, Meta ad spends, and other spends. Now, how is it going to build the model? It's going to take one feature at a time. It will try to first explain sales with one feature taken alone. So it will try to first explain sales with respect to just the Google ad spends, then the Meta ad spends, then the other spends, and whichever of the three gives the best result based on a model performance measure, it's going to keep that feature. So let's say it's Meta ad spends. It'll come up with an equation like this. So sales being predicted with the help of Meta ad spends alone, because amongst the other choices that we gave as an input, only the Meta ad spend piece seemed to be best associated with sales. But if you have other choices left and you have to take one more feature, then it's going to compare between those two features. Now the remaining features will be added one at a time to this equation that we just got to find out the next best feature. And let's say that turns out to be Google ad spend, then you will update your sales equation like this. So this is kind of building a model, taking one feature at a time. So it can work forward or it can work backwards. We can keep on adding more features and we can decide how many features we want and stop at that point. So the stopping criterion here would be how many features do you want? Let's say we wanted only 2 features and we had maybe a number of choices like 5, 10, or 15. The moment we reach 2 best features, we'll stop our model. So we discussed an example of forward sequential feature selection. If we talk about backward sequential feature selection, it has a lot of similarities with the recursive feature elimination because you'll be creating a model with all the features and then you'll be dropping features. But there is a fundamental difference between the two approaches. The backward sequential feature selection focuses on eliminating the features that minimally impact the model performance, whereas the recursive feature elimination performs a feature ranking based on their importance or coefficients, and it removes the least important ones. Next, we'll move to the hands-on piece and we'll see all of these approaches in action. So the data set that we're using for this exercise is known as the Parkinson's data set, and it has been attributed by this research paper, which is known as Exploiting Nonlinear Recurrence in Fractal Scaling Properties for Voice Disorder Detection. This is a data set contributed by an Oxford researcher, Max A. Little and team, and these are the features. So essentially, to give you the background of this data set contains voice samples. Of course, we do not have the voices here. We have the frequencies and other pieces of information in a structured format available, in a row column format available with us. But the end objective of using the voice samples and various attributes from voice is to predict whether a person is healthy or is suffering from Parkinson's disease. It has around 200 rows and about 23 features in total. So we'll work on this data and find our way to choose the best features using the feature selection module and try multiple techniques here. So we are at the Google Colaboratory now, and I have already pointed to the data source, which is Parkinson's. We begin by importing the basic libraries, NumPy, Pandas, Matplotlib for basic visualization. We'll also be performing scaling because some of these techniques are sensitive towards the scale of the variables. Then this is the module that we're going to focus on primarily, which is feature selection from scikit-learn. To begin with, we'll do variance threshold and gradually we'll move on to other techniques. We will, of course, be interested in looking at the model performance. And for that, we are taking up the cross-validation score. And we can choose various models. To begin with, we'll stick to logistic regression model. And then we will also be looking at the model performance measures for which we are using F1 score. Now, we are not going to go too deep into the data pre-processing here because that's something which has already been discussed in several other videos. We'll stick to the idea of feature selection here. Nor we are going to focus too much on the nitty-gritties of the models and their prerequisites. We'll take a simple model and continue to work on it. So to begin with, let's just import all the necessary libraries and read the data using pd read CSV. This is the file that we got from Kaggle. And we are just separating X and Y features because that's how scikit-learn models essentially expect the inputs. So there is a column called name, which is the first column in the data set. Of course, that will not be a predictor of whether the person has Parkinson's or not. And there's a column called status, which is the target column. So these are not the X features. Name is not a predictor. And our Y variable is status. So we are separating it and we are storing it as Y separately. So let's just run this and let's look at the shape of the input data frame, which is 195 rows and 22 features. 22 excluding the target. If we include the target, it'll be 23. Now, variance threshold is sensitive towards the scale of the features. The calculation of the variance, if you know, involves the magnitude of the feature. It's always sensitive towards the scale. So we don't want to give any undue advantage to a feature based on its scale or the choice of measurement. And that's why we are performing a scaling technique. Why I'm using robust scaler? Because we've not really looked at the presence of outliers. We don't want to do that here because that'll be a digression. In such cases, when you may have outliers in your data, you may proceed with a robust scaler, which does the scaling based on the interquartile range. This is something we've explained at length in our data preparation videos in case you've not watched, but let's just do the scaling so that we can work on the scaled data. So the entire data has now been scaled. All right, before we begin the feature selection hands-on, here's a quick overview of the machine learning steps that are followed in any machine learning cycle. And why we need to know this is because this is how the feature selection works. So feature selection is at all stages going to focus on the outcome and accordingly choose the features. Let's get a quick overview of the machine learning cycle. So it starts with the raw data. And at this stage, we are primarily focusing on preparing the raw data. That's what the data pre-processing is all about. Then we move from the stage of raw data, which is prepared, to the algorithm. So eventually you would want to fit a model which is able to make predictions. It could also be that you're trying to study the patterns in the data, and there are algorithms for that as well. So once we call the algorithm, we perform model training. Basically, we try to find the binding relationship between the independent features and the output or the response. Once we are done with this, we try to make predictions. And once the predictions are made, we get the results. So what makes feature selection particularly more powerful is the fact that feature selection is focusing on how good is the binding relationship between an independent variable and a dependent variable. Some of these approaches would talk about actually fitting a model and then evaluating the model's performance, while some of the approaches would talk about just performing a test of a relationship between independent variables and the dependent variable, maybe one at a time, each independent feature with the target column. Now, why we are talking about this right now before the hands-on is because you need to understand that there would be use of a model in this process, and there would be also something that's known as the evaluation. But do you need to know them in depth right now? The answer is no. So be familiar with the fact that we're going to use a model called logistic regression model. If you're already aware of it, well and good. If not, again, you don't have to worry about it. You can imagine this is some process which is going to find the binding relationship between X and Y. And the model performance measure that we'll be repeatedly talking about is F1 score. And at this stage, you don't have to worry too much about that too. But just keep one thing in mind. There are techniques which talk about just studying the independent feature space and dropping the features which are found to be redundant. Whereas feature selection focuses on the end objective as well, tries to see if the independent features are good enough to explain an outcome, if that's the end objective. And if the features are ineffective, then those features will be discarded. So this much background is needed for the hands-on piece that you're going to see next. So in feature selection, we are starting with our first technique, which is known as the variance threshold. Now, as you know, variance threshold is going to check for each feature. If the variance of a feature is less than the specified threshold, the feature will be eliminated. And that's called feature selection. And we are trying a couple of threshold values. So threshold is a value that we need to pass. It has to be a value between 0 to 0.5. And we don't know what is the right value to begin with, so we are trying over a range of values. And what we are doing is, we have created an empty list where we'll keep on updating the selected feature count. So based on the threshold, we'll get to know how many features have been selected, how many features we should retain in a way. That's what we'll be capturing here. First of all, this is a classification problem. And in a classification problem, when you want to give equal importance to recall and precision, you may want to use F1 score, which is a harmonic mean of precision and recall. So we can bring our customized scoring functions using make scorer. We're giving the input here as F1 score, and then we are creating two more empty lists. First is the list of F1 scores for each of these thresholds, and second is median F1 score, because we'll be doing some kind of a cross-validation, and for cross-validation, we'll get multiple F1 scores. We'll take the median of all those. This is an iterative task because we are going to repeat the same exercise for every single threshold that we choose. So we are saying for each threshold in the list of thresholds, these are the values, for each value in this list, we are going to do the same task. We are going to call the variance threshold from the scikit-learn feature selection. We will pass the appropriate threshold. Then we will do a fit transform on the scaled data. And then finally, we will append the select feature counts, which is here. This will be updated as per each threshold. And shape 1 means we'll be selecting the number of columns. Then we are fitting the logistic regression model, and we are doing the cross-validation score, which needs the input as the model, the feature set, which is the X and Y, and which is the X feature set we are giving here, the one that has been fit transformed after the variance threshold application. We are doing 10-fold cross-validation and taking a custom model scoring parameter. Once we do this, we are going to update these two lists. We will update the F1 score corresponding to each threshold, and we will update the median F1 score corresponding to each threshold. Now, if you got this much code here, which might seem a little complex at first, it is essentially making our life a lot easier. So let me run this and we'll see what is the outcome we get when we apply this. So we are creating two plots. First is a plot where we are going to look at a relationship between the number of features selected against the threshold. So for each choice of threshold that we made here, in this case, how many features were finally chosen. And then we are also analyzing the F1 score corresponding to the number of features. So based on the choice of features, how does the F1 score look like? These are the two plots that we are creating. First is going to be a simple line plot, and second is going to be a box plot. And we are using plt.subplot to create these plots next to each other. Pretty basic syntax. Let's just run this, and here's the outcome. So see, from threshold 0 to 0.1 to 0.2 to 0.3, there was no difference. We continued to work with all 22 features. But when we changed the threshold to 0.4, we were able to cut down one feature. When we further changed the threshold to 0.5, we are able to cut down 3 features from the overall features. We had 22 features to begin with, but threshold of 0.5 suggests that we can work with just 19 features, which means we can get rid of 3 features. And how does this number of features that we select affect the performance of the model? So we've created these box plots based on 10 cross-validation scores because we did a 10-fold cross-validation here. So coming back, you can see the choice of number of features on x-axis and the F1 score on y-axis. Now, if you see the number of features as 19, it has nearly the same median, in fact, a slightly better median performance compared to the rest of the features. If you want to exactly see what these values are, we can actually create a table for that. So what we are saying is that we will take the threshold, we'll take the feature count, and we will look at the median F1 score. Let's see. So if you see for the other choices of the number of features and thresholds, the F1 score is identical, 0.88. But for 19 features, actually a lesser number of features compared to the overall features, we have a better F1 score. Isn't it good that with 3 less features, we are able to get a better F1 score? So 0.5 is a better threshold choice here, and 19 is a better number of features for us to work with this data, and it gives us nearly 90% F1 score. So like I mentioned in the beginning, in this case, we are only focusing on the feature selection module. We are not focusing on train, test performance, and other comparisons. Focusing only on the technique, this just confirms that this as a threshold and these as the number of features give us the best result. Now let's move to the next technique, which is known as select k-best. So all the other imports stay identical for libraries. The only additional importing here that we need would be the select k-best class and an evaluation method. So if you remember the grid I showed you in the theory videos, if you're solving a classification problem, and if we are dealing with features which are numerical, we can use the fclassif method. We've explained other scoring functions in that video, so you may refer to it. So these are some of the steps that we've seen earlier as well. We have read the data, we have separated x and y, and we checked the shape of the data frame, just the x variables, and we perform scaling. So these steps stay pretty much as is, and we will now focus on the select k-best. So for select k-best, we need to try different values of k, and we don't know what exactly is the right value to begin with. So we can take from smaller values to a maximum value that will be the total number of features we have. So we have 22 features, that's the maximum we can take. And a smaller, we can start with something like a 5 or 4 or so. So we've started with 5 here and taken a couple of other values in between. We are once again updating a list, which will be selected feature counts based on the k-best. We have the same make scorer like the F1 score we saw earlier. We are appending 2 lists. One would be the F1 score based on the number of feature. Other would be the median F1 score, which we can compare which exactly is the best F1 score. Again, this is a repetitive exercise. So for each k in the set of k values that we have here, we are going to call the k-best, and we are going to do a fit transformed on the scale data, and then we are going to append the list with the number of features selected. We are doing a logistic regression model, doing a cross-validation here, exactly the same way as we saw earlier. and then we are appending the F1 score list and the median. So let's run this, and then we'll be looking at an outcome that will be just one plot, which will tell us, based on the number of features, what's the distribution of F1 scores like, those 10-fold scores that we get. So you see this. On the x-axis, we have different number of features, and on the y-axis, we have the F1 scores. Now, if we want to find out what exactly is the best number of features that we may want to go with, we can just create this data frame. We have populated all these lists above, which talks about the number of features and the median scores. So let's just do this, and we'll get the outcome. So if you see, with 5 features, our F1 score is 87.5. With 10 features also, it's 87.5. With 15 features also, it's 87.5. With 20 features, it's a little better. And with 22 features, again, it's one and the same. So if you see here, you're using 17 less features, and the difference in F1 score is barely 1 point something. So if you think this difference is tolerable, then you can manage your work with relatively much lesser number of features, less than 1/4 of the number of features, and get a comparable output. And if it strictly matters that you want to go with a better F1 score, you can even manage with 20 features. Why would you go for 22? Maybe we can try other values in between as well. So the point is, we may not necessarily want to use all the features to get the best result. We can work with a limited subset of features and get a comparable outcome. That's select k-best. Moving on to recursive feature elimination. Again, all the other imports stay identical. We are just calling the RFE class. And how RFE works, it fits a model and then recursively tries to drop the features one at a time. So the initial steps are all identical. We've read the data, we've separated X and Y, we've checked the dimensions, and we have performed scaling. Scaling is not mandatory for a lot of models, but in general, if you perform scaling, it's not going to harm in any way. So we've just performed scaling here. And let's now go ahead and apply the RFE. So for RFE, again, we don't know what are the best number of features. This is an input that we need to give as a hyperparameter. So we are saying we'll create a list of features. We again created an empty list to update the feature count, created a scoring function, created 2 empty lists to update the F1 score raw values and the median, and same loop kind of a thing, where we are saying for each choice of number of features in the list of features, we are going to apply RFE. RFE requires the model as the input, requires the other input as the number of features to select, which will come through this list. Then we do a fit transform, and then we append the number of features as per each choice. And then finally, we fit the logistic regression model cross-validation score with 10-fold cross-validation and append these 2 lists. Actually, this line here is somewhat redundant because we are directly passing that number of features here. So it's going to take one and the same values, but it's okay because it's more or less in sync with the rest of the methods that we followed. So we'll just go ahead with it. Finally, we would want to be looking at an outcome where we will see, based on the choice of the number of features, what's the F1 score like. And we want to see that box plot. So we are plotting that here. So if you see, starting from 5 features up to 22 features, this is how the F1 score varies. And if you strictly want to monitor the median F1 score, we can populate that in this data frame. These lists have already been appended above, so we can just get the output. So again, for this, if you see, it's nearly the same kind of outcome. For 5 features, you're getting about 87.5 F1 score. For 10, again, that's one and the same. So between 5 and 10, obviously 5 is a better choice. If you want to take it slightly better, even 15 features give you as good F1 score as 22 features do. And of course, we can explore the values in between 10 to 15. It doesn't mean that we have to always take a step size of 5 from 10 to 15. We can try 11, 12, 13 as well. If any number of features, which is a smaller number of features, gives us a comparable F1 score, that will be the choice. We always try to keep the model simple. So we can once again see we could have managed with much lesser number of features than 22 features to predict the Parkinson's disease. Next, moving on to select from model. Again, just the class here, and everything here in this code is identical. We are reading the data, separating X and Y, applying the scaling method. Yes, select from model would require a threshold value to pass. And it compares the coefficients of the features or the feature importance with this threshold and all at once. And if there are features which have their coefficients of feature importance less than the threshold, they're all dropped at once. So again, it's an identical process. We are creating the scorer. We're creating these 3 lists. First, to update the number of features. Second, to update the F1 scores. 10 F1 scores for each threshold. And then finally, just the median score for each threshold. We're doing a select from model. It requires the input as the model as well as the threshold. So only difference you see here in these codes is that there is a choice from the feature selection module. It has its own specific requirements. In case of RFE, this was the model and the number of features to be selected. In case of select from model, it's the model and the threshold to be selected. And now you do fit transform and you append the list for the number of features. And then finally here, we can do a cross-validation, tenfold validation, append the FN scores and the median. So let me just run this code for select from model and then run the second line of code as well. We are all set. And let's look at the outcome, which is going to be a box plot. Once again, it gives us the spread of FN scores for the choice of number of features based on the threshold that we gave. And let's look at the best feature count that would have given us the best median FN score. And in this case, you see, actually, the number of features as 8 gives you the F1 score, which is equivalent to 22 features. So the question is, in that case, why would you use 22 features if 8 features are able to give you that much? And please keep in mind, this is based on the grid that we passed here for the threshold. So if you think we can try different values of thresholds here, maybe a smaller or a bigger value, you can always try to alter that and settle for even lower number of features if needed. Generally, if we increase the threshold, the number of features will reduce. So that's why as we move from a 0.1 to a 0.5, you could see the number of features selected here have reduced from 22 to 8. So if we increase that threshold further, the value might further reduce. Next, we move on to sequential feature selector, and we will look at the same steps here, once again, reading the data, and everything is same, which we've already discussed a couple of times. Let's just apply the feature selector here. This is the identical code where we're given the number of features and we've done the make F1 scorer. This takes a little more time because it's going to try multiple models with varying number of features. So you may have to be a little more patient with this because it for sure is going to take relatively more time. But if you see in the meanwhile, these steps are very identical. The only change is this class, which is sequential feature selector, which requires us to pass the model, requires us to pass the number of features and mention the approach. So we are doing it in a forward way. For backward, in a way, we've already seen recursive feature elimination. So we are doing sequential feature selection, starting with no feature to one feature to more features one at a time. And that's how we are moving forward. And then now let's run this and see the outcome. So we have an outcome where we again have a similar plot, number of features as we move from 5 to 21, or we could have taken 22 also. And then we have the median FN scores. And you can see the median already visually is high for these lesser number of features, right? 5 and 10 have a better median compared to 15, 20, and 21. If you exactly want to see the values, you can actually print this, and this is how it comes. So with 5 features alone, we have 93% F1 score. And with 21 features, the F1 score has come down by about 4%. So what is better? Lesser number of features are better here. So with this, we see there are multiple ways to reduce the number of features. Now, one thing that might bother you at this stage is, okay, so we've been able to cut down the number of features significantly, but how do I know what all features have been selected? This would pretty much be the same for all the classes available in scikit-learn feature selection module. And I'm showing it to you for sequential feature selector. So if this is our feature selector, which takes the input as the model and the choice of the number of features. We found 5 to be a good choice. We are going with a forward method and a cross-validation of 10. We simply fit the robust scale data to this. Again, scaling may or may not be mandatory depending on the choice of algorithm. Now, in order to get the feature names, we need this sequential feature selector, let's say this SFS, and then we will call a method called getSupport. And we are passing this to x.column. So as far as the feature names are concerned, those would not be different when it comes to whether you scale the data or not. So that's one and the same thing. There we are just looking at it from an index perspective that we want to get the names of those specific features which were shortlisted based on what? This sequential feature selection. So if we get a list of those, it displays these 5 features that we finally shortlisted. And you can try the same approach, the getSupport thing, for other classes in the scikit-learn feature selection module. It should work fine for you. That's pretty much about the feature selection module. I hope you get a lot of clarity on how you can cut down on the unnecessary features and work with the bare minimal that gives you a great result.